definition 91, we'll say that a set is inductive, so we'll say a set J is inductive if and only if the following conditions hold. 0 has to be in J, and whenever something is in J, the next of that something is in J. Or maybe I can write it with quantifiers. I mean, it is written with quantifiers. Whenever is a universal quantifier, but I mean symbolically. So for all n, if n is in J, then the next of n is in J. So an inductive set is essentially a set that has the properties that we were trying to attribute to n in this weird circular attempt at a definition. So an inductive set is one that contains 0 and contains the successor, the next, of anything that it contains. So you can think of it like this. We're sort of defining a syntax where what we're defining is the predicate sort of is inductive, right? Or you could say we're defining the adjective inductive, but I'm going to define the predicate because in mathematics, in the language that we're building, what we're doing here is constructing a proposition, right? A way of building propositions. So you put any term you want here, and then you can say is inductive, and then this will be a proposition. So that's the idea there. And semantics, I don't know, let me try to draw a picture. So let's say I depict my sets by drawing a blob and putting dots in for the elements. So to say that this blob is inductive is to say that it contains 0. That's the first condition. And then the second condition is whenever it contains something, it must contain the next of that thing. So, well, it then must contain 1, and so it must contain 2 since it contains 1, and so it must contain 3 since it contains 2, and so on. That's what it feels like we're setting up here. But an inductive set can also contain other things, right? Like maybe there's this other thing named Bob that is in there, and maybe Bob is not 0 or 1 or 2 or 3 or any of those things. And for it to be inductive, it would also have to contain the next of Bob. And since it contains that, it would have to contain the next of Bob. And I don't have friendly names for those things like I do for the next of 0 and the next of the next of 0, but I can still write these things, and if this blob is to be an inductive set, then it has to contain all of these things. So an inductive set at least contains, as a subset, what we think of as the set of natural numbers, which we have yet to define. But it might contain extra junk. There's nothing preventing it from containing extra junk. So if a set is inductive, then it seems like it contains the things we want the natural numbers to contain. But it might also contain extra junk. So how do we define the set of natural numbers? We define it to be the inductive set that contains no extra junk. So basically, only the stuff that we want. So a set that contains 0, that contains the next of anything that it contains, and that is as small as possible while doing so. That does not contain anything that's unnecessary for achieving those two goals. So here comes the definition. So this is definition 92. N, this new constant that we've introduced, is defined to be the set of things that are necessary for a set to be inductive. So remember, inductive means contains 0 and is closed under succession. You could describe this. If you take the successor of any element, then you get another element of the set. And N is going to be the set of things that are necessary for being inductive. So the set of, let me use the symbol little n, since that's a common choice of variable for this purpose. The set of little n's such that if you take any j that is inductive, anything that is inductive, then n is in there. N needs to be in there for j to be inductive. So this is the collection of all of those things that are needed for inductiveness. Now, small warning before I proceed. remember how axiom 5 has a little bit of a bug in it? And that bug allows you to prove a contradiction. I didn't show you how you can prove a contradiction with it, but we did mention that there's a problem, and we're kind of trying to ignore the problem in order to do set theory as people did it before they noticed the problem. To fix that problem, there are certain certain definitions that need to be revised, and that need to also be equipped with additional axioms that help us get around the bug. And this is one of these moments where, if we were not doing naive set theory, if we were really trying to not have that bug break things, then we would have to introduce some new axiom here at this stage to get things to work. Okay, so that's a comment that you can ignore but keep kind of in the back of your mind for later if you ever work out a version of this stuff where you fix the bug. So for now, let's see if we can prove that when we define n in this way, that it has the desired properties. That, well, what do we want it to do, really? We want it to be inductive, right? So if we want to think of n, let me write in green here, since that's my color for loosey-goosey semantics stuff. We want to think of it as this set, 0, 1, 2, 3, etc., right? That's how we want to think about it. So, for one thing, it should be inductive, right? It should contain 0, it should have this property, and it should have the next of anything that is in it. And on the other hand, we also want it not to have any extra stuff. So we want it to be that anytime you take an inductive set, this is inside it as a subset. That's a way of saying that this is the smallest inductive set. So these two things, properties that we want to ensure n has, these are the content of theorem 93. N is inductive, and if you have anything inductive, then n is inside it. So n only contains what's necessary for inductiveness. By the way, pay attention to the title of this theorem, essence of n. My titling convention is that when I say essence of, I mean this is actually probably what you're more likely to use when you need to prove something about n. Probably you're going to use these two properties that it has rather than the original definition. And also, the original definition is designed, it's rigged in order to ensure that you end up with these things. In fact, in practice, what you'll find for the rest of the quarter, as we're going to spend the rest of the quarter doing this stuff, working with natural numbers, and what you will find is that actually it's theorem 94 that you're going to use. So theorem 94 repackages these two statements into a format called mathematical induction. And this is what you will use over and over again when you work with natural numbers. So maybe it's really theorem 94 that should be called essence of n. But I'm giving the name to this one since this is the sort of compact way of saying pretty much the same things that are being said here. Okay, let's get to it. So theorem 93.1, n is inductive. So we have two things to prove. So sometimes what I like to do when I have two things to prove, or multiple things to prove, is just set up the claims, separate claims, and then just so I don't forget about one of them. So let me go back here. Is inductive. To say that something is inductive is to say it contains 0 and that it has this property that it contains the next of anything that it contains. So I have two things to prove. One, I need to prove that 0 is in there. And two, I need to prove that for all n, if n is in there, then the next of n is in there. Right? So pause if you need to and verify that these are the two things that need to be proven in order to prove that n is inductive. Now, for now, let me get this claim out of the way since I think this will take some space. So let me just give it the space it needs. And let's think about our goal. So let's do some scratch work. So the goal is to prove 0 is in n. But what is n? It's the, we'll go back to the definition of n, the set of all things that are in every inductive set, right? So instead of writing j is inductive, let me just write j ind. That means j is inductive. For all j, if j is inductive, then n is in j. That's the membership condition. That's what n must do in order to be in the set of natural numbers. I'm trying to prove that 0 is in this set. So then, axiom 5, I'm trying to prove that this membership condition holds when I put 0 in place of n. So here's my goal, really, unpacked. It's to prove that 0 is in every inductive set. So this is a universally quantified statement that I'm trying to prove. UG is going to be my approach, right? Consider any inductive j. Now I know my first line. Consider any inductive set j. Now I must prove that 0 is in j. But I'm already done, basically. Look, to be inductive, 0 must be in u, right? That is the definition. Then 0 is in j. So, now completing the universal generalization, for all j, if j is inductive, then 0 is in j. Thus, 0 is in the set of natural numbers, which is the set of things that have this property, right? The set of things that are in every inductive set. Great. That took a lot less space than I thought, honestly. Okay, and here's our other claim brought back. So this is a universal, so I know exactly how to start. I should write proof after the claims, I guess. I know exactly how to start proving a universal. It's a universal generalization style, right? Consider any natural number n. Oh, by the way, did you notice how I read this statement in English? Instead of reading it as n in n, or little n in big N, I read it as natural number n. That's how we refer to elements of this set. Elements of the set are called natural numbers. When I say consider any natural number little n, that's just a way of saying this, basically. Okay, scratch work time. So my goal is to prove next n is in there, right? Okay, but this is going to take a lot more room to write down. It's the set of things that are in all inductive sets, right? For all j, j inductive implies that thing is in j. Okay, but this is going to be a little bit confusing if I call this n. So maybe I would have been better off using a different variable here than n for the bound variable. So put maybe x here and here. But it's not a big deal. I can handle it. My goal is just to prove that this holds when next n is put in place of n. So really my goal is to prove that for every inductive set, next n is in it. That's my goal. Okay, I know exactly how to prove a universal. Start a universal generalization. Consider any inductive set j. And now my goal is to prove that next n is in j, right? How do I do that? Okay, somehow I'm going to have to use the definition of inductive. So let's go back. Inductive, what I know about j is that 0 is in it, and whenever something is in it, the next of that thing is in it. Do I know that n is in j? If I knew that n is in j, then I would know that next n is in j, and I would win, right? Do I know that n is in j? Well, I know that n is in the set of natural numbers. I have not really unpacked that yet, so maybe I should unpack that. Since n is in the set of natural numbers, what does it tell me? It tells me n is in every inductive set, right? That tells me that for all j, if j is inductive, then n is in j. That's what it means to be in the set of natural numbers. Axiom 5. Okay, well then in particular, n is in this particular j, right? This is an inductive set. So universal instantiation. In particular, n is in the j that we're talking about here, which is not the same as the bound j here. That's just a way of saying that n is in every inductive set. In particular, n is in this j here. Okay, since j is inductive, to be inductive, you have to contain the next of anything that you contain. Since j is inductive, next n is in j. Okay, so now I can conclude that for all inductive j, next n is in j. So now the universal generalization is complete. N remained, or j remained arbitrary. So here's where, so there are kind of two universal generalizations here, right? I'm talking about the one that starts here. Consider any inductive set j, and here's my conclusion. Let me write it in blue. So for all j inductive implies next n is in j. Yeah. So inside these brackets here is a certain universal generalization, and it ended here. Now, therefore, this is what it means. So the purpose of this was to say that next n is in n, right? This statement here, written in blue, is just another way of saying next n is in the set of natural numbers. And so we started with, you consider any n, and then we proved next n is in there. So we've proven this universal. So we can end here. Great, n is inductive. So anytime you're wondering, is 0 a natural number? This theorem is the answer, if you're wondering. It tells you, in particular, since it says n is inductive, it tells you that 0 is in n. If I ask, I don't know, let's suppose I want you to prove 2 is a natural number. How would you do that? Well, 0 is a natural number since n is inductive. This is by theorem 93.1. And then 1 is a natural number since 0 is a natural number and 1 is the next of 0, and n is inductive. Right? An inductive set contains the next of anything that it contains. So if it contains 0, it must contain the next of 0. And then 2 is a natural number since 2 is the next of 1, and 1 is a natural number and n is inductive. Okay, you get the idea. So theorem 93.1 here is the theorem that tells us that all of these things that we're writing down here are really natural numbers. They are elements of this set that is defined in definition 92. All right, let's work out theorem 93.2, which probably looks less exciting to you, but it is actually what's going to power mathematical induction, which is going to allow us to do everything. It's, I would say, equally important to know not just that n is inductive, but that it's needed for inductiveness. So that's how I think of this, that n does not contain any excess things. It contains exactly those things that are needed in order for n to be inductive. Okay, here's theorem 93.2, and I'm kind of writing a little bit of a shorthand. So j ind means j is inductive. So the theorem says if j is inductive, then n is a subset of j. And you see here, j is a free variable, right? So there's an implicit for all. It's like for all j, if j is inductive, then n is a subset of j. So this is saying n is contained in every inductive set. N is a subset of any given inductive set. So this is implicit for all j. Of course, n is not a free variable, right? Because it's not a variable, it's a constant. This is one reason that it's really important not to write n for n. This one is a capital letter N, right? So this is a variable, since all of the letters of the alphabet we're using as variables. That's why this has a special symbol. All right, now assume the hypothesis. So assume J is inductive. Consider any, so now we're trying to prove this inclusion, right? So consider anything in the left side, consider anything in N. So consider any natural number, in other words. Okay, let's unpack what it means for it to be in there. My goal is to eventually prove that little n is in J. Let's unpack what it means for little n to be in there. Then, using the definition of n, so let me just write it down so you can see it and stare at it. The definition is that it's the set of things that are in every inductive set. Right? That's the definition. So then, using axiom 5, this condition holds with n in place of n. Okay, since that's a little bit confusing, I mean, it's totally okay, but I just want you to be able to see more clearly what steps I'm taking. So instead of n, let me use x. That's perfectly fine. So consider any x in there. Now my goal is to show that x is in here. Then, since x is in there by axiom 5, for all j, if j is inductive, then x is in j. Well, the j that we have here is inductive, so in particular, we have x is in j, since the j here is inductive. Since j is inductive. Okay, but again, since j is inductive, back to the definition of inductive, j contains 0, j contains the next of anything that it contains. So if j is to contain... Oh wait, no. Okay, just needed to prove that x is in j, right? I already did that. Yep, done. Never mind. I don't need to use the definition of inductive. Just, I considered any x in the set of natural numbers, therefore x is in every inductive set, in particular it's in j, so any x in n is in j.